Good morning, everyone. Welcome to the National Workshop on Computational Biology and Chemistry Tools for Drug Designing. Goal of scientist is to explore the mechanism of chemical-biochemical reactions. This implies detailed understanding of the reaction mechanism. This knowledge is required to reduce the reaction barrier, improve stereoselectivity, increase product yield, suppress undesirable side reactions, or to develop a new drug for the unknown diseases. Understanding the mechanisms of biochemical reactions has been an important and active area of computational chemistry. Now look at this picture. What do you identify? Yes, it explains the current scenario. Virus enters into the body and affects the lungs. Currently, humans are immersed in a pandemic caused by the emerging severe acute respiratory syndrome coronavirus 2, SARS-CoV-2, which threatens public health worldwide. To date, no drug or vaccine has been approved to treat the severe disease caused by this coronavirus, COVID-19. Hence, we need to focus on the main virus-based and host-based targets that can guide efforts in medicinal chemistry to discover new drugs for this devastating disease. The role of biochemists is very important in understanding the actual mechanism of the biological activity. This will guide them to discover the new drugs that work against the target. Computational chemistry helps to deduce the mechanism of chemical reactions. It provides the possibility of calculating the properties of transition states and reaction intermediates. Gaussian series of programs initially developed by Popple and colleagues, and the development of density functional theory (DFT)-based computational methods. Originally developed by Kohn with a lower computational costs and reasonable accuracy, compared to post-Hartree-Fock methods, facilitates the wide applications of computational chemistry. Popple and Kohn received the award of Nobel Prize in Chemistry in 1998. Their contributions significantly promote the practice of computational chemistry, not only by theoreticians, but also by experimentalists for comparison with their experimental observations. Intrinsic reaction coordinate (ERC) calculations helps to deduce the reaction path. The initial geometry is the transition state, and the path can be followed in one or both directions from that point. The forward direction is defined as the direction the transition vector is pointing when the largest component of the transition vector, phase, is positive. It can be defined explicitly using the phase option. By default, both reaction path directions are followed. This is top-down approach. The same can also be done by bottom-up approach. Starting from the reactant and product, one can look for the transition state. This will be very helpful where it is difficult to imagine the structure of transition state. We are going to look at one type of reaction path. We, the chemists, call it as tautomerism. The reactions or interconversion between two structures that differ by the placement of an atom or group. A well-known example is the keto-enol tautomerism. Ketone is converted into the corresponding enol form by a proton transfer. Proton transfer reactions are very important in biology. We are going to look at a similar kind of proton transfer in thiol and thioniform. The thiols are sulfur analog of alcohol. Many cofactors, non-protein-based alpar molecules, feature thiols. The biosynthesis and degradation of fatty acids and related long-chain hydrocarbons is conducted on a scaffold that anchors the growing chain through a thioester derived from the thiol coenzyme A. Remember, the role of protein thiols as scavengers of hydrogen peroxide and antioxidant enzymes. In this demo lecture, I am going to show you how to look for the transition state of thiol-thione tautomerism. See here, heterocyclic thiols are tautomerized to thiones. Here, I have shown the structure of methimazole, a well-known example of antithyroid drug. So, we are going to take this tetrazole compound for the calculation.